Okay, so when we talk about collisions, we have kind of two categories in which we qualify them into. We have collisions which are inelastic and collisions which are elastic. Okay, and so here's kind of the difference. In an inelastic collision, these are collisions where things hit each other, maybe they stick together a little bit, they the shapes deform. So like you see a car crash, the cars hit each other and the cars crumple. Okay, well that's an inelastic collision. A collision which is elastic is a collision in which kinetic energy is conserved. Okay, which means no energy is lost. All right, now let's go back to the example of a car crash. So you have two cars that crash into each other and they get all crumpled up. Okay, well, energy goes into crumpling the cars up. Okay, so work is done by the bodies of the cars to slow the cars down in the collision, and energy is lost that way. Okay, or if you have two objects that bounce off each other and make a noise, okay, then some energy is lost that way too. Okay, or really, all collisions, whether they stick 100% together, so you have two objects that slide and stick together and keep moving together, that would be a totally inelastic collision. Okay, and then we have this whole region of partially inelastic collisions where maybe the objects don't completely stick together, but at least they maybe partially stick together. And then at the very end we have this region of elastic collisions where no energy is lost in the collision and kinetic energy is conserved. Okay, now we don't experience in reality any perfectly elastic collisions because always some energy is lost. If you think about the Newton cradle, okay, you lift up one end and they bounce together. Every time they hit together, you can hear them click, and that's energy being lost as sound. And so it's an almost elastic collision, but it's not quite elastic. Okay, and so elastic collisions happen. Another great example is with pool balls. Okay, you hear them click together. It's mostly elastic. Most of the energy is conserved in that collision, but not all of it is. The only real perfectly elastic collisions that happen are those between molecules, say in a gas, that bounce off each other, and in those collisions, not only is the total momentum conserved, so if we have two molecules, they bounce off each other, all that energy they had is conserved, and their momentum is conserved as well. Okay, now we're not going to get too deep into elastic collisions, but the reason why elastic collisions are important is because in situations where kinetic energy is conserved, you can actually predict what the motion of the two particles will be after the collision. With a collision that's partially inelastic or completely that's basically a collision that's not completely inelastic, so anywhere in between here, we can't actually predict what's going to happen. In order to do problem solving, we have to know something about afterwards. Okay? So we're going to look at an example now, a problem. We're not going to really do much to investigate elastic collisions. This is going to be an example of an inelastic collision, but the reason we're using this one is because it also is an example of where we need to look at energy and momentum at the same time. Okay? And if you wanted to measure the speed of, say, how fast a gun could shoot a bullet, well, one of the ways they could do that is by shooting it into a block of wood, such as this one right here, that's being suspended, and seeing how high up that block is lifted. Okay, because what's happening there is you have momentum of this bullet and block system. You got a inelastic collision when they stick together, and the velocity of them combined, that is going to give them kinetic energy, and that kinetic energy is converted to potential energy as they lift up. Okay, so we basically here have a conversion of kinetic energy into, or let's say transformation actually, into potential energy. Okay, And so if we know how high this block is going to lift, then we can solve for how fast the bullet and block are moving together after the collision. Okay, so in this case, they have the same mass before and after they lift up. Okay, we know that the height that they lift is 6.3 centimeters or 0.063 meters. Okay, so go ahead and find how fast the block and bullet are traveling together after the collision happens. Okay, so we solve this. We find that the velocity of the bullet is about 1.11, or sorry, the bullet and the block together is about 1.11 meters per second. Okay, and so that means that's how fast they're moving after this bullet hits this block. Okay, so the second piece now would be, well, how fast was the bullet going itself before it hit the block? Okay, so we have the bullet, it's flying along, it collides and sticks to the block. Okay, and we know how fast they travel together. Well, this becomes now a momentum problem. We have the momentum of the bullet before, and actually let's use a lowercase b for the bullet because it has less mass. And then we have the momentum of the block before, and since they stick together, afterwards we have the momentum of the bullet and the block. Okay? So for the bullet, it's just m times v, and for the bullet and the block, it would be m plus m for each of them times the velocity of the bullet, okay, and the block together. This was that 1.11 meters per second. Okay, and then of course we ignored this. The momentum of that block initially is 0 because it's at rest. Okay. So as we do this, the block had a mass of 5.4 kilograms. And the bullet has a mass of 9.5 grams or 0.0095 kilograms. Okay, for that one and for that one. So now we can go ahead and solve for this velocity. So go ahead and find the velocity of the bullet before the collision. Okay, so we find that the bullet has a velocity of about 632 meters per second. That's actually really, really fast. It's almost, I think that's almost 1,400 miles per hour, which I don't know if bullets actually go that fast, but anyway, so we've now used kind of a combination of energy and momentum to find the speed of a bullet here.